right, so this data table is given to us describing a tank. Okay, so this tank is 10 feet high. That doesn't mean that the liquid inside is 10 feet high, but the tank is 10 feet high. The area has cross sections described with area of A. We don't know what shape they are. They are just simply area A. It could be a rectangle, could be a circle, could be some oval, but it doesn't matter. It's area of A, measured in square feet. The function is continuous, so we have continuity, but does not mention differentiability. Okay, so keep that in mind. It decreases, A decreases as H increases. That means that the area of the cross-sectional slices get smaller the higher up you go in this tank. Okay, so this tank is narrowing as we go up. Selected values for the area based on the height are given in the table. All right, so question 1. Use a left Riemann sum, and when we see Riemann, we think what shape? Rectangles. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. All right, so we're going from area to volume. We're going to approximate that using LRAM, indicate units of measure. All right, so we'll work through this together. So part A, we are going to say that we are doing LRAM. How many LRAMs can we get out of the given data? We can get 3, so you'll indicate LRAM with a little 3. And the LRAM is, okay, so we take our first base, which is 2, and then our left area, so if we're looking at 0 and 2, our left is going to be 50.3, so it would be 2 times 50.3 plus the next base is what value? 3 this time, okay? So the next one is 2 to 5 with a left value of 14.4. And then our last base that we're considering, it would be 5 of 6.5. And then you'd use your calculator to evaluate that. That gives us a total of 176.3, and they want us to indicate units of measure. And so what would our units of measure be if we're approximating volume? Volume? Cubic feet. Okay. That's a 2-point question, 1 for showing the work and 1 for getting the right answer. All right, question B. Will your approximation, or does your approximation from part A overestimate or underestimate the actual volume of the tank, and explain your reasoning? Okay, will it underestimate or overestimate? Well, we need to know what direction our values in the table are going compared to whether we're working from the left or the right. So if we go back and we look at our data table, our values in the data table are going from 50.3 to 14.4 to 6.5 to 2.9. So what direction are they going? They're going down. And we are working left to right. So you should be able to picture that in your head. If you have to sketch it out, that's fine. But imagine that your points are going down like this. And you're working from left to right to create all of the rectangles. So you're going like this. And then you're working left to right and left to right to create your 3. And so you would argue that this is what kind of an estimate? This is an overestimate. So part B, since the values of A of H are decreasing, and we are working left to right, or you can just say we're working with LRAM, the value 176.3 will be an overestimate. Of the actual volume. That was just a 1 point. Okay, your estimate and your reasoning. Okay, part C. The area of these horizontal cross sections in height h feet is modeled by the function given by f of h. So we have this exponential function. Based on this model, find the volume of the tank. So now we're getting more accurate. Instead of just using rectangles to find the volume, we will have another way to find the volume using what math? How are we going to find, given this area? So we had area given to us on a table. Now we have area given to us in a function. How can we be more accurate?
Math 9.
Yeah, we're going to use an integral, and we'll use math 9. So part C, we're going to show that we're setting up an integral. So the volume is going to be the integral of the area over the course of this interval, which is 0 to 10. So you always integrate area to get to volume. So really what you have to write is 0 to 10 of f of h dh, not a of h. A of h was what we used on the table in our LRAM. F of h is what we are using now. So you can just write f of h. If you want to, you also can write in parentheses 50.3 over e to the 0.2 h plus h quantity dh. You can also write it that way. You don't have to. You just any of those simple integrals will do, and then you jump to math 9. There is no possible way for you to find the antiderivative of that by hand. They give it to you, are giving it to you as a math 9. That's what their expectation is. And so that turns out to be 101.325. And again, that would be feet cubed. So compare the two. Yes, we were way overestimated. Our original was a 176.3. Our integral is much more accurate. We were wildly overestimated by a lot. But that stands to reason. We were only doing 3 rectangles. If we'd had more data, if we had 6 rectangles or 10 rectangles or 30 rectangles, we would have had a much more accurate answer. But with only 3, you're going to have quite a bit of inaccuracy. All right, last question, and that was worth 2 points as well. So we've had 2 points, 1 point, 2 points. So that leaves us with our last part. So water is pumped into the tank. Now, when the height of the water is 5 feet, the height is increasing at a rate of 0.26 feet per minute. Using the same model from part C, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. Okay, use the rate. The rate of what? Go back and read it. Which rate are we finding? I don't think so. Okay. Find the rate at which the volume of the water, not the rate at which the height of the water is doing something. Find the rate at which the volume of the water is doing something based on part C. So we want the derivative with respect to time now of the volume. So looking at what I had in part D, I want the derivative of the integral of 50.3 over e to the 0.2 h plus h quantity dh. Going from 0 to, and don't put 5 in yet. Okay, please don't put 5 in yet. Okay, that's a costly mistake to put 5 in. If you put 5 in now, what would the derivative? It would be 0, because you would be going from 0 to 5, which is a constant value, and the derivative of that would be 0. You want the derivative of this. So now you're gonna, this is testing, do you know how to do the derivative of something that has an integral in it? So remember, what then happens when these two things combine with each other? Okay, they negate each other, right? They cancel, the derivative and the integral cancel each other out. And so you are left with the fundamental theorem of calculus that says what you're left with is 50.3 over e to the 0.2. And then what do I plug in? I plug in x. Plus, what I plug in is x. And then what do I have to remember to multiply by? The chain rule. The chain rule applied to x was what I plugged in. So that would be dx dt. So I end up with the quantity times the chain rule. And then minus, you plug in 0 and you multiply, so that's minus 0. So, you know, technically it's there, but it was 0. Now you can plug in the number 5. And now you can plug in 0.26 for dx dt, because that's the rate at which that is changing. So we'd have 50.3 over e to the 0.2 times 5 plus 5, that quantity, multiplied by 0.26. And then that will give us our volume, which is 1.694. And the units on that are the derivative of the volume changing. So our volume is cubic feet changing per minute. Yeah?
Where did the 0.26 come from?
I believe it was given to us in part D, right here.
Oh.
Right there. So you might look at that and be like, okay, like I was good in part A, I was good in part B, I was even pretty good in part C. Part D is where maybe I got hung up a little bit, and that's okay. Okay, remember you're trying to get 5 or 6 points on every FRQ. Yeah?
I might be really dumb right here, but when you're plugging in the 0, isn't e to the 0.2x 1? So wouldn't it be 50.3 over 1?
Yes, but then times the derivative of 0 is 0, so that will wipe it all out.
Okay.
Good question, though.